Okay, in this video I want to quickly go through the solutions to lesson number 4, and I understand that this is the most challenging assignment for the week. However, I wanted to present these to you so that you may be able to take a look at them before you leave for the long weekend and perhaps review them over the weekend. First off, our objective here is to find the rational number roots to these polynomials. Now, if you're unfamiliar with a vocabulary term, of course, I want you to ask for help in class, but since I haven't been there, looking up these definitions online is a pretty good idea. So I just did a search for rational numbers and clicked the first website, and it came up with the Math is Fun website, and their description's pretty good. A rational number is any number that can be made by dividing one integer by another. So integers are numbers that have no decimals or fractions associated with them. They're essentially whole numbers that are positive or negative. And in case you were unfamiliar with that, you can also click on these links, and I believe they'll take you to other sections of their website that'll tell you more about them. So here's a description of what integers are and even a list of them. So the interesting thing about these polynomials that we're starting to learn about is that a polynomial, which is much more complicated than a quadratic that we've seen earlier this year, they can have many different solutions. In this case, there are going to be 4 solutions to this particular example because the exponent's 4, and finding those solutions can be hard. One of the first things that we do is we look for rational number solutions or rational roots, and from there, if we need to find more, we'll continue our investigation. Our focus for this week and probably next will just be to find the rational number solutions. And so if you follow the video that I had posted, we talk about the rational roots theorem. And in this particular case, our p-value, the constant at the end of the polynomial, is 36. And our q-value is 1, the leading coefficient in front of this largest exponent. In number 2, we had a p-value of 3 with a q-value of 1. In number 3, we had a p-value of 56 and a q-value of 1. And in number 4, you might argue that the p-value is 0. However, that doesn't work for our rational roots theorem. So what we ended up doing is factoring out a greatest common factor of x. And in doing so, the polynomial that was left behind allows us to use our rational roots theorem. And we use a p-value of 4 with a q-value of 1. Now, the most challenging part of using the rational roots theorem, let's jump back to number 1 here, is that for your p and q values, you have to list all of the numbers that divide p, all of the numbers that divide q, and then every element from this list in p must be divided by every element that's in this list of q. Well, as it turns out, for all 4 of these examples, when your q value is 1, then the p divided by q, the elements of p divided by the elements of q, will always be the same as the list you created in p, or the list that you created for our p value. Once we have that list, this is saying where all of the solutions might be. Where are our rational number solutions, or I should say, where might our rational number solutions might be? And they're in this list if they exist. So no other rational numbers could be solutions to this polynomial unless they live in this list. So from here, we simply check every single one. In this case, we have factors of 36, which are positive and negative 1, 2, 3, 4, 6, 9, 12, 18, and 36. So it's kind of tough to do and a little bit time consuming, but we evaluate the function at each of those numbers. And what we're hoping to find are examples like this, where we evaluate the function at one of the numbers in the list, and the function ends up equaling 0. That tells me that the number 2 and the number negative 2 in this case are rational number solutions, and another name for solutions are roots or zeros. We sometimes call them zeros because the equation equals 0. Now, hopefully you recognize that because this exponent was 4, that there should be 4 solutions in total to this problem, and there are 4 solutions. It just turns out that 2 solutions are rational numbers. That means that the other solutions in this polynomial are not rational solutions. They could be irrational numbers, or they could be imaginary or complex numbers. And we'll spend time at a later date discussing those. If you follow the same process as outlined in the prior video and as what I just described here, you'll find that in problem number 2, we only had 2 factors of 13, 1 and 13, both positive and negative form. And if we investigate the function evaluated at 1, -1, 13, and -13, none of those end up equaling 0. So none of the solutions to this particular equation are going to be rational solutions. We'd have to use another technique to find the solutions. Now, I'll note here that this is a quadratic equation, a quadratic function. So we certainly could use the quadratic formula when evaluating the solutions for this guy. So I would encourage you to do that, in fact. Use the quadratic formula with an a value of 1, a b value of 6, and a c value of 13 to find the solutions, and you will find that none of the solutions that are obtained are rational numbers. They could be irrational in the form of some square root, or they could be imaginary in the form of a square root of a negative number. For number 3, it behaves much like number 1, where we have lots of factors to investigate. But like number 2, none of the factors end up equaling 0. Sorry, none of the predicted solutions end up equaling 0. None of the investigated values produce a 0 from the function. So what that means again here is that there are no rational number solutions. And so what I would ask you to do is graph this function and take a look at it and see if it makes sense why the claim is that there are no rational number solutions to this particular example. Now lastly, in number 4, once we factored out our GCF of x, we are left with a quadratic inside here. And we can use the rational roots theorem in this particular case. And when we use the rational roots theorem against this polynomial, we see that the potential solutions are positive and -1, 2, and 4. And as we investigate that list, we only find a solution at positive 2. So there's only one solution from that list, but we can't forget that this was a factor as well out front. And if x was equal to 0 here, then this 0 times whatever the inside result would be when x is substituted with 0, the product would also equal 0. So we have another solution there. And so we've got 2 solutions from our potential list of potential solutions. But here again, we were supposed to find 3 solutions in total. We found one at 0 and at 2. And I'd like to note in a special case here that the third solution actually comes from, or is visible, more easily found if you were to factor this completely. Now, if we look at this quadratic, it is factorable, and I'm showing this in red down here. X squared minus 4x plus 4 would factor into x minus 2 times another x minus 2. And since this x minus 2 factor occurred twice, we would say that the solution at 2 has a multiplicity of 2. The solution at 2 occurred twice. Therefore, it has a multiplicity of 2 because it occurred twice. So the 3 solutions are 0, 2, and 2. That seems a little bit unusual to say that this answer accounts for 2 solutions, but that's exactly what we would say in this case. Now, I understand that this explanation will likely not be sufficient for complete understanding. Therefore, we will revisit this material next week when I'm back in the classroom, and I'll do my best to help answer any questions as they come to me in the meantime. Hopefully, I can get this up to YouTube before you all leave for the day, and you can send me any questions that you have. Thanks for watching.